Okay. So let's start from directionality. So everybody knows that the big fish eats the small fish typically. So there are strong constraints in body size um, that determine the possibility of an interaction or the chance of observing an interactions. So if you have a complete random network, what you expect is that there is no directionality. There are a lot of loops in the network, so there is a good chance that I eat you, you eat somebody else, and that somebody else eat me. What you typically see if you have like this strong hierarchy is that you should not see these loops, right? You should not see these cycles, because if you are bigger than me and I'm bigger than somebody else, that's you can eat me, I can eat the other guy, but the other guy cannot eat you because he's much smaller than you. So if you impose these constraints, what you can imagine to study is a system where the interactions where species are arranged on a one-dimensional axis, representing, for instance, body size, and they can only eat something that is smaller than them. And actually, what we are assuming is that species have a fixed probability of eating anything that is smaller than them. So provided that is smaller, they can eat it, and that's the only thing that matters. So if you look at the properties of these networks are acyclic graphs, so there are no cycles. If you look them in terms of metrics, you have predator-prey interaction, so the matrix has a positive coupled with a negative element. Let's say positive are in red and negative and blue are negative entries. And and so it has this structure, right? You can always rearrange the elements such that on the upper diagonal parts there are only positive elements, and the bottom diagonal part are only negative elements. Great. So let's take a big matrix like this, and then what you see is that depending on the parameters, but you typically see this picture. You have like eigenvalues that are on a circumference, and then there is some sort of ellipse centering 0 if the diagonal limits are 0. And we call this spectrum the eyeball because it looks like an eyeball. And one interesting property is that you can actually take this matrix and separate the mean minus the residuals. So you take the average upper diagonal parts, the average lower diagonal parts, and then you take the spectrum of that, and then you take the spectrum of what is left. You can see that you can decompose the spectrum. So if you know something about linear algebra, there is no reason why it should be the case, because these two matrices don't commute. So the sum of the eigenvalues of these two matrices, the sum of these two matrices, the eigenvalues of the sum of these two matrices are not related with the sums of eigenvalues. But this is an interesting properties of random matrices that is color is related to small rank perturbations. So if you take a random matrix and you sum a matrix with a small rank, you expect that small rank only affect that a few eigenvalues are the ones corresponding to the eigenvalues of the small rank matrices, and the distribution of the others are left intact. So in this case, the matrix A is full rank, but a lot of eigenvalues are very close to 0. So they basically don't affect the eigenvalues of the residuals, and vice versa. The eigenvalues that are much larger than 0 are not affected by the residuals. So actually you can decompose the two. And just one important thing, of course, the matrix B, which is a matrix of the residual, is not a usual random matrix, because in principle the two variances, both the upper diagonal part and the low diagonal part mean 0, but the two variances can be different. And in principle they can be correlated. So it's not a trivial problem for none of the two. So actually this is like fairly simple to solve the eigenvalues of this. This is a deterministic matrix, and by recursion you can get the eigenvalues. If you want, it can be an exercise. This is much harder, but it can be solved. So let's look at this. So basically this matrix, what you can find is that the eigenvalues of these deterministic parts lie on a circumference, and the side depends on the mean. So if you have a negative mean, the circumference is on the negative real axis, positive mean is on the positive real axis. When mean, I mean, when with mean, I mean what is the global mean of these two, whether the reds are larger than the blues or vice versa. What about B? Well, actually what you can see is that the eigenvalues of B are also uniform in an ellipse, even if the variances of the upper and the lower diagonal are not the same. And it's possible to do a calculation based on the replica method to find these eigenvalues. Okay, so if you compare the result of the dominant eigenvalue with randomization of this matrix, so what you can do is that you can take this matrix and then you can randomize the coefficients. So you can destroy the directionality. If you completely randomize without keeping the pairs, so you don't conserve the fact that there are like plus coupled with minus, you get these eigenvalues, right? So they are much larger than what you predict. Then this is if you have correlations, and of course, sorry, the green is if you preserve correlation but you still swap, you see a larger eigenvalues. And then if you do the right simulations, when you don't randomize, you get the right prediction. Now you can also consider, instead of considering simulated network, what you can do is that you consider an empirical network structure. So we took 15 food webs, we randomized them, we parameterized them using methods that are based on allometric scaling, and this is what you get. So if you try to predict the eigenvalues with the formula obtained for trivial random metrics, you failed a lot. If you keep correlation, you do some better. But actually, if you use this formula, you are very close to the right solution, which means that the effect of the empirical network structure is it's very similar to the effect of having this hierarchy. Of course, there are other things that are not taken into account, that are the statistical properties that are present in empirical networks and that one can try to take into account, but this shows that there is a hierarchy of mechanisms, right? So if you include directionality, you strongly improve your prediction. And then what you can do better than that is sort of marginally better. Great. So this concludes the first part on directionality.